thank you very much for inviting me to this conference and for organizing this interesting conference on ultrasonic vocalization. I would like to present today an analysis of aversive calls through entire lifespan of rats, from newborn pups to adult rats. This presentation will try to answer the question how those calls are changing in the maturing brain. Rats emit many different ultrasonic calls, from newborn pups, like here are shown on the left-hand side, during postnatal day 2, then the postnatal day 15 and 65. Those are different types of calls and generated by in different situations. There is astonishing number of diseases used in studies with rats. Emission of ultrasonic vocalization was used for modeling anxiety, depression, schizophrenia, autism, and many other diseases. The problem is whether all those vocalizations, which are signaling emotional states, are equivalent to each other at different stages of development. They are distant developmental stages from neonatal to adult rats. So the question arises, are they signaling the same affective state, or those are different states at different ages? The notion that they are all together presenting the same emotional states come from studies using anxiolytics. Here is a slide showing the diazepam, effects of diazepam on ultrasonic vocalization of adult rats induced by during the cocaine experiments. They are craving for cocaine. This is the red line here, and compared to the controls, and for its significant decrease of vocalization after 2.5 milligram of systemic diazepam. By the same token, those are results from pups. From pups, I also have chosen diazepam, which is given subcutaneously, and the big bars show the control and the other increasing doses of diazepam. Since diazepam was decreasing vocalization both in the newborn rats and in adults, the results were, the conclusions were that all of them are representing the same affective state, but it might not be true. So we decided to study all ages of rats and induce ultrasonic vocalization by air puff. This is the stages, this is developmental stages I will be discussing: neonatal to 7 day, postnatal day from 0 to 7, infantile to 20s, juvenile, and then other peripubertal, adolescent, and adult will be treated together. We used air steam device from San Diego Instrument and delivered air puff to rats in plexiglass cage. For pups, we use very small size cage. For adult rats, larger size, but the arrangement was the same, and the same air puff was delivered from about 15 centimeters from the animal. We used about 15 to 20 seconds of stimulation and then break, not longer than for 120 seconds. This is the first result we obtained from neonatal rats. The graph represents duration, of course, in milliseconds, and it was applied every postnatal day up to from 3 postnatal day 3 to 20 days of age. The red line divides the neonatal from infants. Each point represents average for about 11 to 15 animals. As you see, the duration of those calls is relatively constant, about 50 milliseconds, some of them going not more than less than 200 milliseconds. And they are not changing much with age. If we progressed further and applied ERPAF to juvenile rats from the age of 20 to 30 days of age, the pattern changed, duration changed. The average duration of those calls is about 300 milliseconds. This is a big change from the neonates. Minimum was about 200 milliseconds, maximum about 400 milliseconds. So those are significantly longer calls. And there's not much change over the postnatal days from 20 to 30. If we compare those together, here we have neonatal stage, infantile stage, and juveniles. Although there is an overall increase, as the line indicates, of the duration of those calls, there is a clear jump in the duration. Neonates and infants show almost flat, not changing duration, although their calls had very significant changes in frequency, but I will talk about that in a moment. But duration was relatively similar. Now, juvenile had significantly longer. Now, next stage, we move to applying ERPAF to young adults and adults. In this case, we applied ERPAF every 5 postnatal day to shorten the experiment. It appeared that rats from peripubertal and young adults up to the adults emit almost typical 22 kilohertz calls of vocalizations with duration about 500 to 600 milliseconds or higher. And there is, again, significant jump from juvenile calls to young adults and adults calls. That slide shows that those two jumps, so this is not a uniform change over ages, but there is a jump from two jumps shown by red arrows. Now let's talk about frequency. I put everything in one slide, joint slide. So for the youngest pups, the frequency is all over the place. They are emitting calls which have swipes of frequency from very low to very high, and there is no clear pattern in here. Starting from the juveniles, the situation dramatically changes, and from day about 20 up to adulthood, there is a significant decrease in frequency, average frequency, compared to neonates and the pups in the up to 15 days of age or 19 days of age. That insert showed that significant difference. This is again slide showing peak frequency throughout all ages, and the red lines are showing from where the juvenile age starts and from where the young adults and adults start. The rectangle, blue rectangle in the center, shows the boundaries of regular 22 kilohertz calls from about 20 to 32 or 35 kilohertz. And what is interesting, that the juvenile rats emitted calls within those frequencies. So those calls should be, and their duration was 300 milliseconds or longer. So they should be interpreted as short 22 kilohertz calls. While from the day about 35 days of age, the calls were typical for 22 kilohertz calls as to the duration. Those will be long adult 20 kilohertz calls. So we have three clusters of different both frequencies and durations of those calls. We tried to compare those changes with developmental myelination of fibers in the rat brain. The myelination starts like the number 1 indicates about the age of 14, 15 days of age, and then continues. Number 2 indicates myelination of the caudal brainstem. And this is still within that first cluster of pup scores. Now, when the juveniles begin to emit short 22 kilohertz calls, this is a number 3. This is myelination of the midbrain limbic area. It gradually increases and is finished about the day 30 or 29. And then begins myelination of the forebrain limbic system, intensively starting where the number 4 is and continuing until adulthood, until they are 55 days of age. At that point, as soon as the forebrain limbic structures are myelinated, rats begin to emit typical adult 22 kilohertz calls. So the myelination was done by histochemistry, by histochemical staining of myelin basic protein plus counter staining with hematoxylin eosine. And you can see, for example, at the top, the myelination of the habenula, and at the bottom, myelination of typical limbic structure. I've chosen to show you the two limbic major pathway. This is mammillothalamic tract and fornix. At postnatal day 17, you don't see much staining here. At postnatal day 37, there is a clear myelination in those two tracts. So now we need to explain what myelination stage refers to the points where are those jumps when the arrows indicate. So the distress calls, which is common feature of the youngest pups, are driven by the lowest parts of the brainstem. Now the short primitive 22 kilohertz calls, as I would call them, because they are 22 kilohertz calls, but they have some features more primitive, they are shorter, they are not as uniform. And then long, mature 22 kilohertz calls, this will be the last cluster, which is emitted when the full forebrain part of the limbic system finished its myelination. So in summarizing all those results and the comparison of the myelination and the developmental change in responses to AirPuff, I would say that the distress calls are driven by brainstem, the deeper brainstem. Now the primitive 22 kilohertz calls appear when the midbrain limbic system finishes its myelination. And when the forebrain limbic system is finished, the myelination is finished, then adult long 22 kilohertz calls typically appear. Myelination informs us about the connectivity in the brain. So those are the increasing connections between different structures, which are allowing rats to produce those types. So we have those three clusters of calls at different developmental ages, but they are run by different levels of the structures in the developing brain. I would conclude in the following way. Neonatal and infantile pups emit distress calls, and they are driven by brainstem mechanisms. Evolutionarily the oldest part. Juvenile pups emit short, primitive 22 kHz calls, and they are driven by midbrain limbic system. The term midbrain limbic system was introduced in 1950s by Nota. And then peripubertal and adult rats emit long, typical 22 kHz calls, driven by forebrain limbic system, which includes the most classical structure of the limbic system we know. These three patterns of aversive vocalization represent different but related affective states controlled by relevant phylogenetically determined brain structures. We think that those are different states because the parts of the brain which are added during the evolution and connectivity and connections determine how animal will respond and analyze appropriate affective state and resulting activity. At the end, I would like to acknowledge help from Lindsay Shield, Jonathan Samos, and Dale Bellamy. They provided the most materials for this presentation, and support from Natural Sciences and Engineering Research Council of Canada. Thank you for your attention.